All right, thank you very much. So I'm Patrick McFadin. I'm a solution architect here at DataStax, and this is part 2 of a series that I'm doing in data modeling. If you had seen the first one, this is the continuation of that. So our first webinar was on data modeling from more of a basic point of view. But really, I was trying to speak to the relational crowd and say, hey, come on, let's talk about the differences here and bring the relational concepts over to Cassandra topics to try to bridge that gap some. Being an ex-Oracle DBA, I kind of spoke from that experience, so hopefully that will help you if you're trying to make that crossover. But also making the point that we live in this world of polyglot persistence where we have multiple databases and multiple ways to store data, so how does this fit into all of that? We did some basic entity modeling, which is just users and things like that, and covered the relational topics that are pretty hard to conceptualize in Cassandra, and hopefully helped you with that, which is like the one-to-many, many-to-many type data models. And we finished off with some pretty complicated transaction stuff, transaction type modeling. It's not, Cassandra does not do exact transactions, but you can emulate a lot of what you need, but I also argued that you probably don't need as much as you think. So let's just launch right into it here. So today's talk is about being a super modeler, and I pointed out here that I'm not talking about runway models. I'm talking about the super as in Superman, Superwoman. If you'd watched the first and you got kind of the basics, this should really take you to the next level, hopefully, and understand a lot more of just pure Cassandra, how it can do things for you and how you can data model your application. And that's really what it comes down to, is your application has certain specific needs that you can model and express in how you set up your data model in Cassandra. And this is not just a Cassandra problem. This is something that happens with any database. I can make or break a deployment based on a good or bad data model on any database. I've done it before in Oracle. And so this is just really a common concept, but this is specific to Cassandra and how you can make your deployment successful. So let's start out with some basics again, but I'm going to take it to the next level here. So this is another type of data model that's pretty common in Cassandra, and that's time series. Time series is a good fit for Cassandra just based on the wide row format. So we have an example here where we have a weather station that collects regular temperature. So a weather station has a weather station ID, you know, like our airport code, and every minute or every second it collects temperature. And that's a pretty common type of time series application. So the weather station would be my row, and then every new temperature reading would be a timestamp as the column name, and then the temperature would be the column value. And that just continues on. So if I need to find out the temperature for a particular time, I go to the row key, and then I look at which event time that happened, or I can do a slice even. That's a pretty, that's a basic model. But this isn't about basic modeling, right? So how about a super model? Well, if you were collecting your data at every second, you're going to run out of rows. You can do you're going to run out of columns, sorry. You're going to do 2 billion columns in Cassandra, but if you do it every second, I think that's a couple of months worth of seconds. You're going to run out. So we're going to, or it could be even more than that, but the point is there's a limit, and we need to think about that. So this is where we get into the better part of a good time series model, and that's partitioning. So we want to try to put this in some sort of access pattern that we're going to be able to grab, and we're going to partition these rows by day. So now what I've done here is I've created what's called a compound row key. The compound row key is this thing where you see the primary key is, and then the brackets here you have weather station ID, comma, date. Now that means that my row key is going to be, it's going to have 2 parts. It's going to have the weather station ID and date, and that's going to make 1 row key. This is very useful because think about how now I would access this in the data that I have. I go back to what I said in my first webinar. I'd like to create row keys based on information that I have. So in this case, I have 2 things. I have the date stamp or the event time of the event, and then I also have the weather station ID. The weather station ID is the easy one. The date part, what I'm doing is I'm just taking out the date, not just the time part. I strip out the time part. So that means that every day has a new row. And that's pretty cool. So now whenever I go to ask for that data, I say, okay, I want this weather station ID, and I want yesterday from 10 a.m. to 11 a.m. I have all the information just in that query where I can find this row, and then I can go get that event time. Now, the other part of this that makes it cool and super is this business of what I put at the end, where I say clustering order by, and by the event time, and it's descending. What that really does is it's reverse sorting those columns in that wide row. And this is a powerful feature that really makes access efficient. So essentially what's going to happen is it means that the last event that happened is now the first thing in that row. So if I wanted to go back and ask a question, let's say I want to know with this weather station ID on this date, give me the last 10 things that happened, that's an easy query. You just start at the beginning of the row, and then you get 10 things in. And it's very efficient, very fast. But it's also, I don't know the dates. I just want the last 10 things. Perfect for dashboarding. If you're using something like HiCharts or one of those JavaScript charting libraries, you can get some really fast and efficient charting with that. You just say, here, go get me all the last 10 things that happened, throw them in a chart. And so this is a very common type of pattern with weather data, any kind of time series data. But time series data really does well with this reverse sort, because essentially this is how we think of things in time series. We want to know what just happened. Things that happened a while ago, well, we can go look for that later, but most times it's what just happened. So another basic model, now we covered this in our last webinar, just refreshing this thought, is here's a user entity, and it's got one primary key. It's the username, which is there, just one, and it's boring. There's nothing exciting about this. This is a pretty standard table. So how can we make this a little more interesting? Well, the first thing we're going to do is we're going to go down a little vignette here. We're going to go down the path of collections. So let's talk about this new feature. It's in 1.2, and this is something that will really energize your data model quite a bit, and I'm pretty excited about collections. So collections have three types: set, list, and map. And each one has their own properties, and I'm going to go through each one. So this is a nice thing to add to your data model when you have something that needs to be dynamic inside that same row. It keeps you from having to do things like dynamically add new column names, like if you have email, and then email 1, email 2, email 3. It's better to just think about it as, well, I have a pretty static model, but then there are some things that need to be dynamic. Great, we can cover that, and I'll show you how we do it. This is a part of CQL 3, and in, like I said, Cassandra 1.2 and above. So if you want to use that feature, you're going to have to be on that version, which shouldn't be a problem because in open source it's out there, and in DataStax Enterprise it will be out very shortly, probably next month. So next month being June if you've watched this in June. So we have some anti-patterns that we need to talk about here. So one of those is the serialization. So serialization cost is associated with collection, and that's something you have to be aware of. So when I say don't go crazy, I mean don't think of this dynamic part as you're going to dump all your data into it and expect good performance. That doesn't say it doesn't perform well, it's just you need to understand that as you're tweaking your data model. So the other thing is that there's a limit to how many objects you can have in that collection, and that is 64,000. That's a pretty good size number. I think you can work with that, right? So the serialization cost is going to be in probably going to be in your read time more than anything. So if you have some tighter SLAs on your read, think about that serialization cost as an overall cost in your budget for your SLA, like how many milliseconds it takes, and just act accordingly. If you're really tight on milliseconds, then don't put as much data in there because you're going to have serialization costs. If you have a very loose SLA, then have a little more fun with that. So let's go through the specific examples. I've got the table creation here, and I'm showing you how it looks when you create the table. You have the set with the type, list with the type, map with the types, plural. Let's go through each one. So set. Set is just like it sounds, it's just a set of information, but the difference between set and list is how it's ordered. So the ordering in set is by the type comparator. So let me explain that. So you have the name, the collection type set, and then inside the greater than and less than brackets, you have the CQL type. And that CQL type is how it will manage things like sorting a text versus an int, and that's the way you want it to be sorted. So in my example here, I'm inserting into this collections example that's 1 and 2. Now, because I'm using text, it will sort by text because 1 sorts before 2 in the collating order. And that's cool. That's what I wanted. Now, I'm going to go a little more in depth about how you add and subtract data. So if I want to add an element to the set, I do this plus equals business where I say set example equals set example plus the new element that I'm going to add to the set. Now, when I do this, the 3 is going to sort to the end because 3 is just fits in that collating order, and that's fine because that's what I'm using a set for. If you were to say something like set example equals and just the curly bracket 3, here's a little pitfall you should understand is it's going to overwrite that collection. So you need to do the set example plus the new element to just add to it. And that's just, I found that out the hard way the first time I used collections. I'm just going to pass that on so you don't have to do that. So we have also the adding an element to the beginning. And it's really because I know the sort order. I know it's text. So in the second example, I say set example plus 0. Well, because 0 is first in the collating order, I'm going to go ahead and, when I do a select, see that. Okay, well, look at that. 0 is in the beginning because I have that sort order. Now, removing an element is pretty easy. It's just set example minus and then the name of the element in the list, and the set, I'm sorry. And that is a random, so you can do any element inside that set, and it's great. You don't have to pull out the whole thing. That's really what we're trying to avoid, is extracting the entire collection, manipulating it in your own code, and pushing it back into, so that'd be a read and then a write. We don't want to do that. Next up is the list. And a list is where you control the order by how you insert the data. So very similar to the set, you have the collection type list, and then inside the greater than or less than is the CQL type. And that CQL type, again, is it's listed on our documents. You can see there's a lot of them. There's longs, ints, text, timestamps, time UUID, it goes on and on and on. But that's the type that's being enforced, but it has nothing to do with the sort order. So when I look at my insert, now I have these square brackets around it, but this is more like what you would expect in an array. Like, here's the order that I want. 1 and 2, that's the order it's going to be when I do a select. So how do we manage that order? Again, here's some operators on that. So very similar to the set, we have this update collections example, and then I'm going to do list example equals list example plus, and then the 3. So now what I've done is I've added it to the end of the list. Now, not because it's sorted by the 3, but because I said list example plus the 3. So that's append. So then I'm going to do an add an element to the beginning of the list by putting that 0 plus list example. So now if I go to select that, you'll see the 0 first because I said put it in the front. So you're prepending that to your list. That's how you control the order. Now, deleting that is, the order, of course, doesn't matter, and it's very similar to the set where you just say list example minus and then the name of the element inside the list. Now, here's one of my favorites. It's my favorite right now because I think that it has the most use right now, is a map. So a map, of course, is a key and a value, and the key is sorted by the CQL type. So this is something to understand. So in this example here, I have this map and an int and a text. So the CQL type of the key is int, and the CQL type of the value is text. It's going to sort by the int. So the numerical value is going to be that collating order. So if I look at this example where I'm actually inserting it, you can see that I have this map with the curly brackets around it. It's 1 colon and then the name and then text of 1, 2 colon text of 2. It's going to sort by the 1 and the 2. So let's look at the operators on that. Adding an element to the map is a bit different, but it is about what you would expect, because what you're trying to do is just append things into this map. And so this map example, you take the element of 3 and you put it into, and you put in the text of 3, and that will add that to the map that I just created. Now, because it's sorted by integer, that means that it'll sort towards the end. If I want to update an existing element, I call it out by, say, a map example of 3, and in this case, I change it to trace instead of 3. So now it's just going to update one thing inside the map. Very handy. That could be really cool in your data model if you think about that dynamic update that's inside the map. Now, keep in mind, this is important, is that Cassandra has row-level isolation. That means when you do a row-level operation like this, that you get a consistent read. You're not going to get a client reading that row will not get half of the data. It will get a consistent picture. So as you have things updating all these lists and sets and maps, the clients doing the reads will get a consistent list, consistent set, consistent map too, because it's all on the same row-level isolation. Very important. Finally, delete. A little different is where we actually have the delete command. So we say delete this map example and then the element number 3 inside of it. And that will dynamically remove that one piece. So what are we going to do with this? We got this cool collection stuff. How would we use it? How about an example? So back to our user table, which was boring, not anymore. I figured out something that will make it cool. So here's an example of how you can make your boring entity tables a little more spicy with some collection. So I have the static user table, but I'm going to add this dynamic piece to it. And that dynamic piece is this location by date. So I have this requirement in my application. When someone logs in, I want to know where they came from and their IP address and what date they logged in, their last login time, and what date. And I'm going to display that to them or something like that. So it's like bank or something where they say, hey, the last time you logged in was this date, and here's the IP address. So I need to store that along with the user record so I can have a nice denormalized data structure. So I'm going to take advantage of that row-level isolation as well. So I'm only updating one row with some dynamic information, and it's consistent. So if another reader comes along, it'll get a consistent picture. So how am I going to do this? Now, if you notice, also, I'm using a time UUID for the key, and that's the way I want it to sort. A time UUID is essentially a timestamp that has a resolution down to microseconds. The timestamp goes to a millisecond, which is great whenever you're displaying it to a user, but when you use time UUID, you're trying to get uniqueness, and really you need to get down to the microsecond because that's where you start getting the resolution that makes unique work. If you do it by millisecond, lots of things can happen in a millisecond on a computer. So the time UUID is really helpful whenever you're trying to get a unique value, but it also sorts well. And so in this case, I'm going to sort it to like the last thing that happened. So let's take a look at how I would use this. So whenever someone logs in, I'm going to collect their username, of course. I'm going to say, oh, here's your username, and then my application pulls the IP address that they're calling from. Now, what I'm going to do is I'm going to update their user record with this, okay, their last login, after they successfully log in with the user and password. I'm going to use this now operator. And this is a kind of nice shortcut that's included in CQL. And what it does is it creates a time UUID. And a time UUID is, like I said, this unique part with a microsecond. So it's going to pull that information as part of, it's going to use the current information that it has in the system, create this time UUID for you. Now, if I have multiple nows in here, it's going to use the same time UUID because it's when it happens. So that's also very convenient. So what I'm doing essentially is I'm changing the last login to right now, and then I'm adding that now with this IP address. And that's just going to add that to, that's going to insert this new record. So now the next thing I'm going to do is whenever I add that, I'm going to go back and I'm going to be able to see what IP addresses this person is logged into. However, what we're probably going to run into is a problem where I'm going to have a lot of logins. And so if you have someone who's logging in all of the time, you may want to not grow out that list. Again, going back to the serialization cost and maybe even the limit to the size of the collection. So here's my kind of spicy upgrade, which is the TTL. And a TTL is a time to live, also known as an expiring column. And these are some of the best tools to use in some sort of models where you know data can just needs to be disappeared, or you're trying to keep a certain window of information. In this case, I added this using TTL of, and then it's in seconds, and really what that is 30 days. So I get 30 days of data in this map, and then what's really nice and convenient and very useful is that it will magically disappear at the end of 30 days. It's just a great feature in Cassandra because I've built plenty of stupid batch update delete jobs that just goes through and cleans out old data. You know, that clean job that you had to cron up or whatever, that doesn't have to happen anymore. And that's why this is very useful, because we have plenty of times where we just need data to live for a certain time frame, and it's just what do you do with it whenever it's out of that time frame. Cassandra will just deal with it for you. So what I get is this really nice, clean implementation, and so whenever I ask for data out of this collection, I know that I'm only getting 30 days worth. Perfect. Next big topic. So we're moving our data model into one area which has particular interest for me, because I feel like this is where you get a lot of power out of Cassandra, is in creating your own indexes. So when I'm talking about indexes, I'm not talking about indexes like you would do in a relational database. A relational database's indexes are built for speed inside a column, and this is not what we're talking about. We're actually doing some data modeling here where we want to have our application intent expressed in some sort of data model. And I'm going to explain this with some examples, but that's really what we're trying to do. It's like I have to ask a question. Well, that question is now being expressed inside the data model, and that's more or less an index. It says, oh, here's something I'm going to look up, and here's the information that I want. So it's that fast access to a very specific query. So some of you who have some experience with Cassandra or have been around for a while know that secondary indexes exist. Secondary indexes in Cassandra are not relational indexes. Again, relational indexes are built for speed. Secondary indexes are not built for speed. They're built for convenience. And this goes back to the big table paper at Google, where secondary indexes were meant to find a certain column value, because you can have a random amount of columns. It's very hard in a big table model to find a specific column with a value in it. So secondary indexes were like a map to find that. Okay, I have a column name and I need a value out of it. So again, convenience, but not for performance. When you need performance and you're in looking up something, I'll show you how to do it. So my single most important thing to point out about when you create an index to look up data, use the information you have on hand. If your application has a certain set of information, use that. Don't do a get to get more data. Don't calculate things if you can help it. Sometimes you need to, but be thoughtful of how you create your indexes. And the pre-read thing is really probably the biggest thing you don't want to do. So here's our goals with our index. We're going to use a row key. We're going to create a row key that will give us the speed. And we're going to use wide rows for the efficiency, meaning that once you get a row key, you're going to a specific server. That key exists on one server. And then that row exists on that server, and when you use a wide row in the slice, you're minimizing disk seek because you're grabbing it all in one shot. So that's what we want, fast and efficient. So let's go through some examples. So my first one is a keyword index, and this is probably the most basic, and if you've done this before, you'll recognize this. You might also recognize this if you've watched any of my other data modeling talks about my video. I have a video database example out there. So I'm just going to use this again because it works. So what a keyword index is it uses a particular word. In this case, I have an example where when someone uploads a video, they put tags on their video. Cat, LOL, funny. And those tags exist with the video, but what if I have a specific case where I want people to be able to search for videos that have the word cat in it? So doing a random search on Cassandra like that is just an anti-pattern. It's not going to work very well. If you put secondary indexes on there, it's not going to be very fast. That's just the wrong way to do it. And the way to do it is, like I was saying, you want to make it fast and efficient with creating your own index. So in this case, what I'm doing is I'm taking information I have, the tags, and I'm just going to parse them out. So I have my cat as a keyword. I'm going to use that, and I'm going to use that as the key, the row key. So if you look at my table create here, the tag is the primary key, and then the video ID, which is the actual video that it belongs to, is going to create this wide row. That's that second element of the primary key. So every time someone adds a video with a cat in it, it's going to put that video ID in that row and just grow out dynamically. And there's probably going to be a ton of cat videos, right? Because that's what all the videos on the internet have. And it's just going to grow as it needs to. So now when someone says, hey, give me all the videos with the word cat in it, then I'm going to be able to take them right to this one row and then grab a slice. Here's the last 10 cat videos we've uploaded. And it's a very fast query and then efficient when it grabs that slice, because you're just grabbing those first 10 or first 100 or all of them even. But it's all going to be one single seek off the disk and a very fast index pattern. So that's a basic one. So this is actually taken from a real-world example that I worked on, but this is an alteration to what I just was talking about, where let's say that you have a table, a user table, and you want to look up someone by their email address. Now, if you create a secondary index on email, that's not going to be fast. It's going to be convenient if you put a secondary index on the user table. But in our case, we want to make this fast. We want to find someone quickly based on their email address. So the pattern to do that would be to maybe put the entire email in a row key, and then maybe the user ID in a column. But essentially what you're doing is creating a big key value store, which isn't very efficient because you're going to be spreading things all over the place, and it's just not the best way to do things in Cassandra. We want to stick with a wide row if possible. So what I am proposing here is what I call a partial word index. So you take this full thing, this email, and you break it up into parts. So I have this tcod at relational.com that I want to be able to look up. So what I'm going to do is I'm going to break it up into two parts. I have the domain part and then the user part. And so I'm going to use the row key for everyone at relational.com, and then each user at the beginning of that will have their own column in that row. So you might, if you had like a bunch of columns, say, or a bunch of emails up from one domain, you're going to have a lot of users inside of that row. What I would then caution against it if you're doing something like this and you had like yahoo.com or gmail.com, which is a massive domain, then you could even take it down a little further, take some letters out of that username and get a better partition out of that. So you can mix and match this. You don't have to break it off at the @ symbol, but think about the concept here. We're going to take some part of that name and then use that. So let me expand this into a different type of thing just to kind of drive this home. Again, take it from a real-world example. Now I'm going to create partitions based on the fact that I know there's going to be a lot of whatever I have. And so I'm going to try to keep this, I'm going to have a good balance between rows and how many columns I'm going to have. The number of columns I'm going to have is really based on my SLA. The more columns you have, it's going to be harder to keep those smaller access times, just based on the fact that there's going to have to go further out to find the data. If you are working on shorter column values or a shorter amount of columns, then it's a faster access pattern. So there's a balance there somewhere. You know, maybe 100,000 columns somewhere, that 10,000 columns, really based on what you're trying to drive for your SLA. But how do you even get to the point where you can pick and choose? This is how you can do it. So with this product index, I want to know how many parts I have in a particular store. So I have a store number, and a part number, and a count. These are the three things I have. Well, I want the count, but I have the store and the part number. So how am I going to create a lookup key for that? Now, how I'm going to do this is I'm going to create this product index, and I have this, I'm breaking up the part number into four digits. It's a 10-digit number. The first 4 digits are going to be part of my row key, and along with the store. So look at what I've done here with the compound row key. I have a store and then 4 digits of the part number. That's going to be the row key. That's going to keep things partitioned pretty nicely. So the column name is actually going to be part number 4 through 9, so that last 5 digits. But I'm sorry, 6 digits. But now I've gotten a wide row out of that because I have a lot of different parts in there. So when I ask the question here, store 8675309 has 3 of parts 70797485575. I'm going to insert those parts together, the parts of the numbers, and then whenever I ask that question, I get that really fast and efficient query. Now I'm going to be able to get exactly what I need within milliseconds, and that's what I'm hoping to do. It's not a scan on the database. I'm not going to do a full tail scan or a go fetch, or I'm going to have to create an index to make it faster. It's just there. Now this means there's a couple of things that this means is that you're going to have to manage your indexes as part of inserting your data. And so if you're back to my video example with the tag index, if I insert a new video, I'm probably going to have to insert multiple times into a tag index. That's okay. Remember, Cassandra likes to do writes. Writes, it can do all day long, every day, millions of writes per second. So doing multiple writes on a single access is not a problem. Actually, it's kind of encouraged. And that's the pattern that we want to follow. And so using that along with how you create indexes is a really good pattern. Okay, so then my final index here, which is a little more complicated, but hopefully you get your juices flowing on your next model, is a bitmap index. And it's a bitmap type index. I should be very careful. So how does this work? This is not built into Cassandra, by the way. I'm building this myself. So a bitmap index, in my definition, is going to have multiple parts to a key. And I need to look it up by any one of those parts. So I'm going to create a truth table of these different combinations. And I have examples. Don't worry, don't freak out. So when I do this and I have all these different combinations of, say, 3 fields, it means I have 7 different options. That's, of course, there's no null choice. It's just 7 different options. So that means I have to create 7 inserts for one set of data. And if I have 4 fields, I have 15. So what do I mean by that? What do I mean by creating a truth table? Here's my example. I have cars in a lot, and I want to be able to find them. So I want to find out which lot the car is in. So I have 3 things to choose from. I want make, model, or color. And I really want to be able to choose, you can imagine like a web page where you have some drop-down boxes with the make, model, and color, and you have 3 choices. I really want to be able to pick any or all of them, and it's really an or condition. So if I just have the model and the color, I want to be able to find what lot and vehicle ID that is. If I just have the color, I should be cool with that. If I have all 3, again, I'm cool with that. What this truth table is saying is that I need to account for all the different choices in one shot. So I'm really pre-optimizing for the read here. I'm basically creating views. So when I do the write cycle, whenever, let's say, I go park that car in the lot, I have a vehicle ID and a lot ID. When I say, okay, this is where it is, I need to insert that in 7 places and those different combinations. Let me show you how that's done. So I'm going to create this table, this car location index. My first 3 things, make, model, and color, now are going to make up this compound row key. So there's 3 different options in there. There's a vehicle ID and a lot ID that are associated with the car itself. So I created vehicle ID as one of the parts of the primary key, so it will create a wide row. So I have these 3 things, make, model, and color. How does it look on the insert? So I put in all 7 inserts here, and you can see the pattern here, where I have the first one is I insert all of them. And then if there's different combinations all through those 7 different combinations of inserting blanks in one thing. But if you notice, it's just a repeat of the same data over and over with different combinations in the primary key. And so, or the, I'm sorry, the row key. So now once I do all these inserts, I can ask interesting questions. Now on my data model that I created as an example on my own machine here, I inserted a lot of different cars so I could ask some different questions. So what about that? So now when I do a select, I say give me the vehicle ID and lot ID where the only thing I know is the blue Ford. I don't know what the model is. It could be anything. Mustang, Tempo, whatever you want, Explorer. But I know it's a blue Ford. Okay, when I put in that combination exists in a row key. It's one row key that I'm looking up, and it's very fast. And because the vehicle ID is in there as a wide row, it's very efficient. That's my answer. Here's my vehicle ID and my lot ID. Now, let's get even more general. Let's say I just know that it's a blue car. Where are the blue cars at? Okay, now I can get into this where I can say the blue is just in one option. So if you notice, I get a lot more answers that way, which means that if you were to actually look at the column counts whenever you do this, the less options you have on your row key, the wider the row probably will be, because there's going to be more things that fit in that bucket. So you take advantage of the dynamic nature of that wide row by using a data structure like this. Again, this is very specific, but this should hopefully get you thinking about how you can use some very interesting combinations of your data in your row key and how you construct your data model for those fast lookups. That's what I've done. I've optimized this. So that was my last example. So this hopefully will get your game up, you know, and I quoted Yoda sort of at the top here, but this is, I say it saves you because you can really make or break your experience with a bad data model or a good data model. And I hope that you do think about this whenever you do your data model, and think about how it can really make your application using Cassandra a lot better. And I say don't settle for boring. Just don't think you have to throw things into an entity table and then hope for the best and do some, you know, doing some application level joins or things like that. When I see those things, it makes me sad because there's better ways to do it. The worst thing you could do is take, say, a relational model and just copy and paste it into Cassandra. That is not the right way to do things. That is a complete anti-pattern. So what we want to see is a mixture of those things, but really just digging into what Cassandra does so best is distributing your data, scaling out like crazy, but also being online all the time. So with all that going on, think about your data model and how your application can work with that. No downtime is a good thing. So we have one more, and I hope you're going to be there for this. This is at our Cassandra Summit, June 11th. I get the big room, and I'm going to be talking about the world's next top data model. This will be a continuation of this series. That will be the third part of this series. I don't know if there will be any fireworks or anything crazy going on, but I hope to see you there. If you need to be there, because I know you do, look at what we got going on. So first of all, it's a Golden Gate Bridge. It'll be right next to that, actually. But look at this lineup. And I mean, I could go on. I mean, look at the companies that are going to be there talking about how they use Cassandra, and they're very successful at doing this. So why wouldn't you want to be there? Why? Why? Answer that. I don't have any reason. I'm going to be there. So just because, you know, I got a lot of love for you, I gave you a discount code. Use my discount code to be there. And here's the added bonus is that we are doing expert tables. I will be there. You bring your data model. Let's talk about it. I will be all over the place, but you know, I really want to talk to people. This is why I'm going. I'm doing 2 talks, and the third talk, or the second talk I'm going to do there is about our new drivers. So I really want to push 2 things here. Data model is important. Using our driver is going to help you get there faster. And our driver is out. It's in general availability. Here's the link. We're Mikhail Figueroa and I are going to do a presentation, joint presentation on this on June 12th, the second day. And we're going to talk about all these things I've been talking about data modeling. I'm going to tell you how to do this with code, how to build your application with this. And we're really, it's amazing some of the things that our new driver can do for you. I really hope that you can be there. So that's it.